If you're sitting the Cambridge International AS and A-Level Physics 9702 exam, your grade literally hangs on a razor-thin thread. We're talking about the tiny difference between a decent guess and a mark scheme perfect answer. Today in this explainer, we're tearing down exactly how to secure those top marks, and we're using the crystal structure chapter as our ultimate testing ground. No fluff. We are pulling directly from the examiner playbooks to show you exactly where points slip away.
Okay, let's jump straight into a two-student duel. We've got two exam answers here, and they're fundamentally talking about the exact same physical reality. The first one reads, cubic systems have atoms. This makes them strong. And the second one reads, atomic packing controls bonding direction, determining macro-level defect tolerance. One of these is written in everyday casual language, and the other, well, it speaks the exact dialect of the Cambridge mark scheme.
So, which student survives? I want you to predict the winner right now in your head. The stakes here are absolutely huge. The student who wrote the first answer is about to face a massive confidence shock when they get their paper back. They're going to lose critical marks, even though they felt like they really understood the concept. The other student, however, sails through with full marks. Why? Because they understand what the examiner is actually hunting for.
To understand why that first student failed, we really need to look at some painful learner mistakes. You see, ordinary revision totally fails because students just memorize labels instead of linking cause and effect into a disciplined logical paragraph. They state correct terms, words like atoms or strong, but they don't offer any physical explanation of the mechanism. They just throw out real-world applications and leave them completely unlinked to the microscopic reasons. It ends up being a scattered collection of facts rather than a connected chain of scientific reasoning.
Now, in a moment, I'll show you the exact examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. Seriously, missing this upcoming examiner clue is the absolute fastest way to drop critical marks when you actually know the physics, so stick with me. So here is the crucial point. It's a four-step examiner framework that shifts your thinking from basic memory to elite mark scheme reasoning. Step 1, the definition, or the core concept. Step 2, the microscopic mechanism, like what is physically happening down at the atomic level. Step 3, the measurable consequence, what evidence or data do we observe on the outside? And step 4, the real-world application. Delivered with precise examiner wording, if you can force your answers through this exact funnel, you literally leave the examiner no choice but to award you the marks.
All right, let's apply this. We're going to see how this builds when we map it to a micro topic from the crystal structure chapter. Cubic families in crystal systems. We aren't just going to memorize what a cubic family is. No way. We are going to tear it down and rebuild it using our four-step strategy, so you can see exactly how a top-tier answer is constructed.
We always start with a practical phenomenon, not just a dry definition. We want to build true understanding, right? If I ask you, what physical effect does this explain inside a solid, and why does it matter for real materials? I'm forcing your brain to connect the textbook to reality. This is exactly how you lock the information into your long-term memory.
What's really fascinating here is how we're forced to look at the microscopic picture to explain the whole system. In this context, the definition of cubic families is the principle that the macroscopic, visible behavior of a solid can only be interpreted by understanding the internal physical changes happening down at the atomic or carrier level. Basically, the macro is entirely dependent on the micro.
Then, we tighten our everyday language into the technical vocabulary expected in the exam. It's just not enough to say atoms are arranged in a cube. We need the actual mechanism. The specific crystal arrangement controls the atomic packing, the bonding direction, and the defect tolerance. These three phrases, actually, scratch that. These three specific mechanisms, packing, bonding direction, defect tolerance, those are your golden tickets. They are the microscopic mechanisms that cause the material to act the way it does.
And this brilliantly illustrates your memory triggers. If you can answer these 4 prompts aloud right now, the topic is completely secure for your revision. What is it? Well, that's your definition. What changes inside? That's your atomic mechanism. What is observed outside? That's your consequence. And where does it matter? That's your application. Treat this framework like your ultimate revision checklist for absolutely any physics concept.
It's also vital to compare this micro-topic with nearby ideas. You really need to see the boundaries so you don't confuse related concepts under exam pressure. A super common trap is confusing cubic families with a general lattice. You see, a general lattice just focuses on the basic repeating geometry of the points. But cubic families? That requires a focus on how that specific geometry dictates atomic packing and defect tolerance. Knowing the difference stops you from writing a beautifully accurate answer to the totally wrong question.
Remember, the framework demands an application. Connecting the physics to semiconductor wafers or aerospace turbine blades makes the underlying reasoning super memorable. When you think of a structural alloy or a gemstone, don't just picture the object itself. Picture the atomic packing inside it determining its bonding direction, which in turn gives that turbine blade the defect tolerance it needs to actually survive inside a jet engine.
Okay, now it's your turn. I want you to step into the examiner's shoes for a Cambridge-style challenge. We're going to look at 2 more answers, and I want you to actively grade them in your head based on the framework we just built. Take a look at this escalating, harder example. One student wrote, "Turbine blades are strong because of cubic families." And another student wrote, "Cubic packing dictates bonding direction, increasing defect tolerance in turbine blades." One of these is just a scattered collection of facts hoping to scrape a mark, while the other connects cause and effect absolutely flawlessly. So can you spot the exact missing link that destroyed that first answer's chances? Take a second to think about it. It identified the real-world application, turbine blades, and it threw in the broad topic name, cubic families. But what is completely missing?
The examiner correction is crystal clear here, and this is that crucial examiner clue I promised you earlier. You always lose marks when you give a real-world use without justifying the link to the underlying microscopic reason. The failing answer gave an unlinked application. The winning answer won the marks because it explicitly explained what physically happens internally at the atomic level, the packing dictating the bonding direction.
Resolving our earlier duel, the winner is officially revealed. The second student wins simply because they applied our specific scientific reasoning framework. They move seamlessly from the concept of cubic packing to the scientific reasoning of bonding direction to the evidence of defect tolerance, all wrapped up in perfect examiner wording. That, right there, is how you bulletproof your physics answers. But wait, solving this actually reveals a dangerous new problem in your answers. You've mastered the framework, and you know how to link the macro to the micro, which is great, but perfectly applying this framework is only half the battle. You also have to be on the lookout for nasty command word traps hiding in the latest examiner reports, traps that trick even top students into giving the right answer to the completely wrong question. To make sure you don't fall victim to those traps, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. The goal here is to elevate your perspective from a student trying to remember facts to an examiner evaluating a logical argument. Unlocking that next level of understanding requires you to discover exactly which examiner report mistakes will cost you your grade and how to avoid them. That's why clicking the next explainer on your screen right now is your mandatory next step. Go ahead, click over, and I'll see you there to break down those dangerous examiner mistakes.